Hello, everyone. Thank you so much for taking time to join us for our informational webinar today. My name is Corey Hesser, and I am one of the program developers at Kirkwood Corporate Training. Here with us today is Eric Foreman, who will be discussing the impact of shifting to a failure avoidance perspective for your equipment and organization and providing a preview of Kirkwood Corporate Training's Precision Maintenance Master Program, which starts January 2025. Eric joined Hendrix Precision Maintenance Services with over 15 years in industrial automation, maintenance, and reliability engineering, focusing on system optimization and waste reduction. His career is driven by a passion for continuous improvement and empowering people to excel. Eric has held leadership roles in the Midwest maintenance and reliability community, including serving as an NE Iowa chapter president and contributing to SMRP boards for certification and scholarships. He also regularly presents and hosts workshops at industry conferences. So again, thank you for being here. And Eric, I'm going to go ahead and hand it over to you.
Good morning, everybody. Thanks for joining us today. Can you hear me just fine, Corey?
Yep.
Okay. So we're going to talk about today, truly proactive maintenance, moving from failure management to failure avoidance, and what that means. So as Corey said, I'm Eric Foreman with Hendrix Precision Maintenance. Also in a leadership position, I'm the current chair of the Society for Maintenance and Reliability Professionals, Nebraska, Iowa, and then do a lot on the national boards as well. Been in industry since 2005. Went to Central College in Pella, Iowa, for computer science. Ended up with accounting information systems and business management. Honestly, just kind of fell into industrial manufacturing after I graduated. Had some friends that got a job at a manufacturing facility in Nevada, Iowa. Met some people there. Ended up with an internship. Started working on their lockout tagout program, and then that kind of evolved into automation and controls. I've always had a passion for organizing things and data, making decision making, simplifying that, making it easier, continuous improvement, and that's kind of fell into reliability and asset management. Have a real passion for manufacturing in North America. I think that strong manufacturing in North America is ultimately the path towards a lot of things that ail us as a society. I think good manufacturing jobs, high quality products, give people hope in a lot of areas where there, simply isn't hope. So proactive, what does it mean? One of the most common things that I hear, and I said it myself early on, when you go to a maintenance and reliability conference, if you're in a workshop, in a training, you hear a lot of people say that they want to become more proactive. They want to become less reactive. As you're going around a room and people are giving introductions to themselves and where they came from and what their responsibilities are, you'll hear the first person say, I'm here because I want to be more proactive. I want to be less reactive. I want to do more preventive and predictive maintenance and less emergent maintenance. And typically the first person that says that, right after they do, you'll see a lot of heads nodding up and down, and you hear a lot of me toos, a lot of agreement throughout the audience. And typically the outcome that comes from that and where people naturally want to go is towards more preventive maintenance and more predictive maintenance. Just so I want to talk real quick about just natural failure patterns and what a lot of the data suggests with failures throughout industry. And this is industry as a whole, components and assets that have failed, and across all classes, just the common trends that we see in equipment failures. And often what we assume is that the likelihood of an equipment failure increases with age. As something gets older, it gets more likely to fail. And this is often at the core of why our maintenance technicians and teams, reliability teams, have their schedules filled with a lot of preventive maintenance work. A lot of times that's a good idea. The most important thing we do in industry is preventive maintenance, across taking care of the equipment that we have, if it's done right. Unfortunately, there's a lot of preventive maintenance work that is essentially busy work, adds no value. Common studies that we've seen anywhere from 30 to 75% in a lot of facilities of the preventive maintenance work that they do, the tasks that their technicians have their day filled with, aren't adding any value. And that's what we want to get at here. Work that's often done for the sake of an asset at best, and a lot of times for the sake of a metric. They're doing the work to satisfy the PM compliance metric, so they can pass that up the chain. Instead of doing preventive maintenance work, doing the inspections, doing the work that takes care of the wear components of that asset, ultimately for the overall success of the business and the department and production. So this curve that we commonly think of as things wearing out over time is what's called the wear out failure pattern. Wear out is just as it explains there. It's as things get older, as they have contact, they have wear components, they fail, they degrade. Environmental factors, material selection, just the nature of the thing. Filters clog, it can't be washed. Scraper blades, they wear out, they need to be replaced, and things of that nature. And then we also have random failures. These are, a lot of times you'll think of these as, you'll hear people saying, I don't know what happened, or you'll hear things like gremlins. That's never done that before. Things of that nature. And these have no discernible pattern tied to, there's no repeatable pattern, and nothing tying it to the overall age or number of cycles associated with that asset. A lot of times when you have failures that are random in nature, you'll have the source of that being poor operational knowledge. Operational overload is something that's very common here, where it's not a consistent overload. It's a one-off where it's being run outside of the acceptable band of operation. You'll see poor design factors contributing here, items not being designed for the environment, and then poor maintenance practices. A lot of the random failures, if you have the data to dig in and see what the source of your failures are at your facility, a lot of times these failures will be as a result or shortly after some sort of intrusive maintenance has been done. And what often isn't understood, that the next curve or pattern that we'll talk about is infant mortality. When we do intrusive maintenance, when we're tearing down a piece of equipment that's running properly with poor workmanship, we have what's called infant mortality. And anytime we do intrusive maintenance, we reset that clock, or we reset the band. When we start up and something fails at the onset, a lot of times you'll hear things like bad out of the box with electrical components, with bearings, with mechanical seals. Start it up and it fails shortly after. A lot of the sources of failure with this are similar to the random failure, but it's tied to being fresh from startup or shortly thereafter. Poor equipment design, poor system installation, manufacturing errors, quality. They do happen. Motors come in, bearings come in that are bad. Mechanical seals, with the ISO standards, 9001 standards for quality, those aren't as common as they used to be. But there's, a lot of counterfeit parts coming in and things of that nature. So you do need to be aware of this. But more often than not, situations and failures associated with this curve or this failure pattern come from a decision that somebody's made, either in the installation or the operation, incorrect operation, or bad workmanship, just not knowing. Doing a lot of times technicians doing the best they can with the tools and knowledge that they have. So those three curves, three standard patterns: wear out, random, and infant mortality, combined to what's been commonly known, and you may have heard it referred to as the bathtub curve. But those three patterns are the prevailing patterns for how we see failures in industry, in manufacturing. And studies over 35, 45 years, and still what we see today often when consultants go into a facility and they're looking at CMMS failure data, asset failure data. Typically what they see when they compare them, they break down those curves and failures in the facility. There's really two categories that they break them down into: time or cycle based, which would be those wear outs where there's evidence linking the failure of that asset to either a cycle count or a general time count. And then you have failures that are random in nature. There's no discernible pattern that links it to time or cycle count. There's no evidence of it being a wear out issue. And what they established is that across all of our assets, all of our failures that we see in industry, typically we're looking at between 10 and 20% of those failures being time or wear out based, and 80 to 90% being random in nature, where there's no discernible pattern. And of the random failures, infant mortality is by far the most prevalent. The overwhelming majority of the failures that we see, typically between 60 and 70% of the failures that are random in nature are infant mortality. So when we talked at the onset about preventive maintenance, the assumptions that we have with equipment failures, failing with age, wearing out with age, preventive maintenance, a lot of the time as it's incorporated at our facilities, is a lot of times only suitable and effective with the patterns with these wear out components, and not with the infant mortality. When it comes to infant mortality, when it comes to these random failures, human error is responsible for the vast majority of these failures. So our goal needs to be addressing these shortcomings. When we do have failures, identifying what the source is. Is it product specifications? Is it design? Is it standards and procedures? Is it workmanship, lack of tools? And we need to be looking at those things and addressing them with training and certification of our technicians, and with role-written standards and job plans to make sure that the work that they're doing is repeatable and it's being done correctly each time. So I was in a unique opportunity at the SMRP National Conference last year, and it was at dinner, and we had 7 or 8 people there at the dinner table. And just so happened, we had 3 people who had worked for large bearing manufacturers. And a lot of what we do at Hendrix is training around the foundational skills when it comes to precision maintenance, rotating equipment assembly. When you think of rotating equipment, the fuses in those systems, anything rotating, typically your failure point is going to be the bearing. When you think of pumps, you're most likely going to be looking at bearings and mechanical seals. So I had an opportunity while we were at the table to do a very non-scientific study, and asked the 3 guys that were there, what they thought, what percentage of the bearings that they put out into the field actually made it to the L10 life. And the L10 life, for those of you that don't know, is when a piece of equipment is going through acceptance standards and under lab conditions, they put it under ideal operating conditions, and then they run it until 10% of the population, of the total tested population, starts to show some level of defect. And then this is typically what they publish. You'll see a lot of bearings, the L10 life can range anywhere from 10 to 20 years. And that would be the point under ideal circumstances that, a tenth of that population would start to show failures. And I was asking them what percentage of their bearings actually survived, catastrophic failure, taken out of operation, taking a piece of equipment down. And, bearing company number 1 thought it was somewhere between 7 and 12%. A lot of their bearings actually went into OEM equipment, sealed for life bearings, so fairly high. Bearing manufacturer number 2 thought it was somewhere between 3 and 5%. And then the third one at the table said 0. He didn't think that any of their bearings actually made it to L10 life. Is this bad statistical analysis? Or is it bad bearings? What do you think? And when you start looking at everything that has to go right for a piece of rotating equipment for one of these components to have a long life, there's a lot of things that have to be in play, from manufacturing, shipping, receiving, selection. When you think about your team at the facility, are they selecting the right components? When it comes to your maintenance technicians or even your supply shop, a lot of times we send rebuilds out to a rebuild shop, and we assume that they're the best person for the job. We assume that they're trained, that they're certified, that they're going to do it with precision, and they're going to do it the right way. How often do we have an asset come back from one of those shops, put it into service, and it fails shortly thereafter? Or if we do acceptance testing, it fails before we get to put it uh, into production. And then you have lubrication. We kill more assets with a grease gun than anything. Over lubrication, under lubrication, incorrect lubrication, not using calibrated grease guns, contamination, etc. And then operation. How many times do you get out into the field, ask an operator, if a piece of equipment isn't running, you ask them how it's supposed to be running. You ask them what their control standards are for it. Ask them what their settings are. You'll find that a lot of times that they don't know. They've been given a production target, might be overclocking a piece of equipment, might be overloading a piece of equipment, etc. And then you think of maintenance, after it's in there, the things that we do after the fact, outside of lubrication, not having acceptance standards, doing intrusive maintenance. We've had a failure at some point that's furnace, so we're going to make sure that it doesn't happen again. So we're going to over PM a piece of equipment, do a lot of intrusive maintenance just to protect ourselves and make sure it doesn't happen again. But what we're trying to get across here is that most of these failures ultimately come down to a decision that somebody has made along the way. At some step in the process, it's rarely ever is it intentional. Our people in manufacturing, in maintenance, in operations, in production, they are doing the best they can with the knowledge, skills, and tools and equipment that they have available to them. Nobody's trying to fail. They just haven't ever been shown a better way of doing it, or the right way of doing it in a lot of cases. It's the old adage or orientation practice of following Joe around. You come into a site, you follow somebody around for a couple weeks, and then you get put on shift, and you're expected to know everything without having the right training, without having standards and procedures in place that you can follow to baseline your work against. So this is the specified design, install, potential failure, and failure curve, the SDIPF curve. This has gone through several revisions over the last few years. And when we talk about failure management versus failure avoidance, when we talk about moving from being, reactive and always working in emergent work to being more proactive, a lot of times we talk about doing more preventive and more predictive maintenance. And ultimately what that is a failure management practice. We're trying to catch a failure that's already been introduced into the system. There's already some defect into the system that's going to cause that piece of equipment to fail. And we're trying to catch it and replace the component or the asset while it potentially still has some useful life on it before it fails catastrophically and causes us downtime. When I talk about failure avoidance, what we're trying to do is keep the defects out of the system. We're looking to extend the I to P interval. The I to P interval is what's considered, profitable operation of the equipment. That's from the point it's installed and commissioned and released to the point that potential failure shows up. And that's what precision maintenance tries to do. We're trying to extend that I to P interval, the productive, profitable operation of that piece of equipment. And it's nice to be able to fix a car, but what we're trying to do is establish the skills and knowledge, expertise, so we don't have to fix the car. Implementing, making sure that we're specifying a piece of equipment to suit business needs and expectations. We're designing it for the environment, the facility. We're also designing it for maintainability and reliability, making sure that our technicians can get to it when they need to work on it, making sure that they can lubricate things as needed. And then when we install it, we're installing with precision to acceptance standards, alignment, vibration. We're taking baseline readings for vibration, for acceptance, and making sure that that gets recorded into the CMMS. Unfortunately, a lot of our acceptance standards that we see in industry, if it's a pump, we're checking rotation, making sure it's turning the right way, and making sure that there's fluid moving. We don't do a good job of designing and defining expectations for our equipment, whether that's production capacity, acceptance standards, or checking the vibration and having acceptable standards for that. But that's what we're trying to do when it comes to precision installation. And then we want to, it's continuous. This is a growth area. We want to learn from failures, and we want to do more of the good stuff and less of the bad stuff. You're gonna have failures when you're doing work like this. It's inevitable. What we want to do is fail forward, learn from those things, and do a better job the next time. Make it easier on our technicians to make the right decision the next time. So what we know about failures is the overwhelming majority of failures that we see in manufacturing, they aren't wear out. It's not degradation. A lot of times it's a decision that we've made somewhere along the lines. We're killing the asset. If we want to be truly proactive when it comes to maintenance and reliability, which is why we have reliability departments, it's why we have predictive maintenance departments. We want to move as far back on the I to P curve as possible. We want to make sure that we're extending that during the installation phase. We want to make sure that we have acceptance standards. And then when we do fail, we want to make sure we're failing forward. There's way too much parts changing in industry, even when we're doing preventive maintenance and predictive maintenance, condition monitoring. We throw parts at an asset without understanding what's causing that problem. If we have high vibration, we replace the component and start it back up. And oftentimes we'll see that same high vibration, 3 months, 6 months down the line. Where if we installed it with precision, we evaluated our acceptance standards and put it in and installed it to limit that vibration, we'd be a lot better off. We're keeping those defects out of the system. Defect elimination, drive those defects out of the system. And precision maintenance, honestly, anything that we do to make the technician's job easier when it comes to making the right decision, following procedures, having training that's repeatable, that can be applied throughout the entire plant. It really does create an enabling environment as we start to bring more people into that fold. Work expectations, acceptance standards, and team accountability. A lot of times you'll see them start to self-police themselves. The expectation that the technicians set for one another that floor will start to raise, and you'll see some really neat dynamics starting to evolve within your culture. So what we do, precision maintenance, the precision maintenance certificate program. I started working with Kirkwood just before COVID with this program. Was working with the Kirkwood Industrial Maintenance Technology program with some internships. Had been denied approval to have this training for my team here locally, and was trying to find another way. And I knew that our technicians in this area needed this training. There was a big push and you still hear it all the time, Industry 4.0, AI, advanced predictive maintenance technologies, etc. And it felt to me like we were ignoring a lot of the basics. The basic fundamentals of what we do as maintenance and reliability technicians. And what I wanted to do was address a lot of those overlooked, taken for granted fundamental skills. I wanted to get our technicians set up. Our saying at Hendrix is do it once and do it right. Um, we were addressing a lot of the same failures over and over. The thorn in the side issues, as I'd like to talk about them. And I wanted to start eliminating those things. And I had a hunch that a lot of them were due to either precision installation or our lubrication practices and lack of a sound lubrication program. And I wanted to set our technicians up to solve those problems on their own. I wanted to expose them to the right way of doing things and have them start to challenge some accepted assumptions that we had within our facilities. And I wanted them to give them the right information to make the right decisions and challenge those assumptions. So what we put together at the time, I was trying to get Hendrix Precision Skills 1, which is the foundations of rotating equipment assembly and installation. And then Noria, who's a global leader in lubrication best practices and program development. Wanted to bring them together. And then we also were at a large pumping systems facility, and I needed something in for that as well. So I combined skills 1, which is the rotating equipment, skills 3 from Hendrix, pumping systems, fluid dynamics. Recently added skills 4, which is industrial fasteners and precision bolting. There's a lot of aspects of bolting and fastening that are taken for granted, and then the Noria class as well. And then we wrap it all up with maintenance innovators, their certified maintenance and reliability technician prep class and certification. Kind of tie it all together, and then offer the technicians a certification. Hendrix Precision. So I'm not giving this presentation because I work for Hendrix. I work for Hendrix because I feel very passionately about this. I think a lot of the skills that our technicians need, a lot of the things, especially on the mechanical side of the house, that our technicians do have been taken for granted for a long time. Just turning wrenches, just fastening bolts. There's a lot more to it than that, and I wanted to promote that, and I wanted to set as many people up with these foundational skills as possible. So that's ultimately why I joined Hendrix. But Hendrix, we do craft skills assessments and training. Sorry. Craft skills training. We do procedure development, and then also field coaching and mentoring. The foundation for the program out of the space industry. So in the 60s, late 60s, early 70s, there were a couple things happening in parallel. We were trying to beat the Russians to the moon, and continually we had a real tough time getting a rocket into space. The same time, the engineers established that a lot of the failures were due to rotating equipment, seals and bearings, which is what we see commonly in industrial manufacturing. And that as they were able to fix the problems, is the big thing that came out of that is they reduced vibration by 20%. They were able to double the life of that asset, so exponentially increase the life. About that same time, Ralph Buscarella, whose son Greg works for us, was in the early stages of vibration analysis for industry. He was working in a lot in the paper manufacturing industry, and he wasn't studying vibration analysis for the sake of selling logging equipment and doing the analysis. He wasn't doing it for the sake of the analysis. He was trying to drive defects out of the system. So as he was studying the vibration analysis of rotating equipment, he was also trying to dig into the root cause. What was causing that vibration, and how can we establish training to drive those defects out of the system? And ultimately, Ralph's class led to what we now see is Hendrix Precision Maintenance Training. He was kind of the forefather of that. Worked it into the pulp and paper industry. And now the company that Phil Hendricks started was a result of that. Some of the core things, the big things that came out of that program, reduce vibration by 20%, double the life of a piece of rotating equipment. And the correction objectives that came out of that were wanted to eliminate common assembly errors, key lengths, key orientation, things of that nature, soft foot, establish tighter balance specifications from your manufacturers, from your OEMs. What's the balance that we expect to come into our facility? And then what do we do as technicians, as commissioning technicians, installation, internal technicians? What do we do to not disrupt those balance standards? Wanted tighter alignment specifications. Do we just straight edge it? Do we bolt it up? Is our metric for success? Is it pumping? Is it turning? Is it conveying? And as soon as you get there, you walk away. Or do we establish some tighter alignment specifications that'll ensure a long life for that asset? And then also wanted to eliminate lubrication errors. And those are the 4 core things that we cover in our Precision Skills 1 class, and the things that I really want to address with this program for our technicians in this area. You'll see here the reduction from that study. As you're able to reduce vibration by 20%, you double the life of the bearing. And the format that our class takes is on the day 1, we introduce several errors, bugs into a piece of rotating equipment. And then throughout the week, we teach a subject, and then the technicians or attendees go back to the simulator and they remove that bug from the system. And then they're able to monitor amp draw, temperature, and vibration of that piece of equipment. So we tell them a thing, and then we show them how to do that thing, and then we show them how to measure and then correlate that to extended asset life in that piece of equipment out in the field. And that's the thing that really hits home with a lot of technicians. We aren't just presenting to them for 4 days. We're covering the why, and then really digging into the hands-on aspect of it. A lot of the technicians are kinesthetic learners. They need to do something to learn. If you put them in front of a PowerPoint presentation for 4 days, they're going to sleep through it, and very little of it's going to go back with them to the field. If we show them how to do it and then make them do it on their own, so we simulate an equipment outage for the 3rd day, where we strip it down to the base, and then they go through with their team and do it all on their own. There's a lot of learning take up that happens with that. And a lot of that makes it back out into the field and back out into your plant. So I've always thought of continuous improvement. It is kind of a real growth and real improvement. It doesn't happen overnight. It's a marathon, and that marathon we're running is on a treadmill. So we're going to continue to raise that bar for what's acceptable. But what we need to do to start getting better in our facilities is to establish a core set of principles that kind of guide what we do and work to get just a little bit better each day. Find those opportunities to eliminate inefficiencies, identify absence of value and the work practices that we're doing, the things that our technicians are doing on a daily basis, and start chipping away. Stop throwing parts, like I said, with vibration analysis, stop throwing parts at symptoms, and dig in and address the underlying problem and root cause. Eliminate defects. Too often, when we have an improvement initiative, we take on too big of a chunk. What we need to do, and what we aim to do with this training, coming out of this training, is we want to identify the wolf that's eating the sheep and take care of them. We want to find a problem, that thorn in your side. Find one pump, find one conveyor, find one auger, find one fan that's causing you a lot of problems, and go fix that, and then move on to the next one. Chip away a little bit better, a little bit each day. And to be truly proactive, we need to build a team that asks the right questions and challenges the wrong assumptions. And I think if we can do that, throughout this region, we're going to really set ourselves up for a lot of success in this area in manufacturing. So that's all I have. I appreciate your time. feel free to reach out to me anytime. I'd love to talk about any of these items in greater detail. Yeah, thank you very much for your time. Appreciate it.
Thanks, Eric, for presenting that information on precision maintenance today. When I send out the follow-up email, I will attach the precision maintenance master flyer for you all to take a look at. If you have any questions, please reach out to Kirkwood Corporate Training. And I'm going to just launch a brief poll here just real quick. And if you want more information, feel free to enter your information in there as well. And now would also be a great time for any questions if anybody has any. And if not, again, I appreciate everybody attending and taking time out of your day to join us today.